We're actually doing two lessons here. One is just a very short lesson. I'm calling it 9.x, and the reason is that this topic, even though it's really important in this unit, for some reason isn't really touched on in your textbook. They kind of gloss it over as if it's obvious, maybe, or they don't really explain it. So this has to do with horizontal asymptotes. We're going to be looking in this first part of today's lesson at determining the equation of a horizontal asymptote for any rational function. Of course, you know, based on the very first quiz question, that if you're given a graph and the equation of the function is in this form, that the equation of the horizontal asymptote will be y equals k. That's kind of standard practice. But what we're talking about here is any rational function. Okay? And it doesn't have to be in that form. So to begin with, we have a warm-up, but before we get to it, I want to show you and explain to you the difference between a vertical and a horizontal asymptote, and it will help us answer the questions in the warm-up. If I told you that we had graph or function A over here on the left, and there was a vertical asymptote at that particular location, what that means is regardless of what the function looks like elsewhere, it will be approaching either infinity or negative infinity as you get closer to that asymptote. And it could be, we haven't, I don't think, seen any like this in Math 30, but it could be that that's what it looks like in that vicinity. Or it could be that this is what it looks like in that vicinity. It doesn't matter. They could both be down, one up, one down. They could be in this opposite directions. Doesn't matter. But what a horizontal asymptote looks like is this. And one of the things I will point out is that with a vertical asymptote, you can never be on that line. The graph cannot touch that line. But you may encounter functions that do cross a horizontal asymptote. And the reason for that is, it's not a big deal, but I don't want you seeing one of these later and going, wait a minute, what's going on? The reason why that is functions are allowed to go up and down. And all that's important with an asymptote is it's asymptotic far away from the origin. The only way the function on the left can be asymptotic far away from the origin, if it's a function, is that it can't cross this line. Because if it did cross the line, well, that's not a function. Functions don't go back and forth. That would fail the vertical line test. I'm getting a little off topic here, but I think that's important to note that in terms of functions, vertical asymptotes are verboten. Can't be there. Horizontal asymptotes aren't. What is important is this. What's happening, let's pick an actual number here. Let's say this is x equals 4. What's happening with a horizontal asymptote is as x approaches a very large number, y approaches the location of the asymptote. And that's the concept of limits that we use in Math 31 in my other math class. But we don't have to talk about limits here, but I think you should understand what I'm saying here. On the other hand, what's happening here is, if this is x equals 3, what's happening is as x gets closer to 3, y takes off to infinite values. So there's a real different way of looking at it. And we're going to use this idea here, and I'll highlight it for you. We're going to use this idea here to answer the warm-up and then develop a rule. So, a horizontal asymptote is what y approaches when x gets very, very big. So, if I want to know if there's a horizontal asymptote for h of x, I can put that into my calculator, I can go to my table, and I can start putting in very large values for x and seeing if y is approaching some number. Let's do that. So I'm going to put in for y in brackets x squared plus 2x minus 24 over, I'm sorry, I have to get out of this mode. I don't like it. Over, in brackets, 2x minus 5. Double check as always to make sure that you've entered things correctly before you go anywhere else, because you won't be able to see it, but it looks okay. I don't know what my table setup is at right now, but I'm going to go table set and change it to ask. This allows me to put in different values for x. So again, the concept of a horizontal asymptote is that as x gets bigger and bigger, if y starts getting closer to a value, then there's a horizontal asymptote at that value. So I go to my table and I enter maybe 10. Now 10 isn't a really big number. We said as x gets really big, y settles down. When I put in 10, I get that. Well, let's put in 10 times greater. Let's put in 100. I get 52 point something. Let's put in 1,000. I get 500. Let's put in a really big number. I don't care what number it is. It's big, though. And I'm getting 4.29 times 10 to the 8. It's not 4.29, it's 4.29 times 10 to the 8. It appears as though this is just exploding. And by the way, we don't have to look in the left direction in this course. Looking to the right is good enough. You know, if you wanted to, you could look at the graph, zoom 6. You could see that this graph, the first part to the left of the vertical asymptote just keeps going up more and more and more. And this one, more importantly, I suppose, the one on the right, this arc, appears to be going up forever. It doesn't appear to be settling down. And what that's telling us is that for function h of x, there is no horizontal asymptote. I'm assuming that everybody who's taken calculus with me right now can look at that function and know. And you don't need to go limits as x is approaching infinity. You can look at the rule that that leads to, which everybody else doesn't know about yet. Well, let's try the next one. And again, those of you in calculus, you could probably go to sleep for the next 5 minutes because you understand this. The next one is y equals 3x minus 10, and it's over, in brackets, 2x squared plus 35. Again, I'm going to go to my table. I've already got some preloaded numbers in there. I'll just double check that I've entered it correctly. Oh, I haven't, apparently. Oh, I have an extra set of brackets. I'm going to go to my table, and you can see what's happening as x gets bigger and bigger. Y starts getting smaller and smaller and smaller. So that 1.7 times 10 to the negative 9 that you're looking at right now is 0.000000001 something. It's a very tiny number. And if you wanted to, we could, well, continue to put in really, 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 really big numbers. And what we just, I didn't mean to hit graph, but that's okay. I'll talk about the graph right now. You can probably tell that whatever's going on, there appears to be the x-axis is a horizontal asymptote, which is at y equals 0. But if I go to my table, I mean, this is really tiny value of y. This is not a definitive proof. You can't just look at this and go, oh, for sure it's going to approach 0. Because maybe, it's not, maybe you go far enough down the line and all of a sudden it starts rising again. It doesn't really make sense that it would do that, but it's not a proof. So what we would say here is that there is a vertical or a horizontal asymptote, my mistake, at y equals 0. Because, and I don't know that you need to write this, as x approaches a large number, like infinity, y approaches 0. And that's where the asymptote is going to be. If we try the last one, we have y equals, in brackets, 5x squared minus 2x minus 9 divided by, in brackets, 2x squared minus x minus 10. I'm going to clear my table and start from scratch just to show you the progression of what's happening to y. If I were to put in 2 is not a big number, but if I put in 2, I get negative 1.75. If I put in 50, which is a big number, I'm getting 2.5083. I think that 3 probably repeats. Well, no, there's more stuff there. If I were to put in 1,500, just an arbitrary big number, I'm getting that. If I put in that, I get 2.5. Now, just a second. Do I get 2.5? Well, no, I don't. If I scroll over here and look, it's not 2.5. It's just really close to 2.5. So it's approaching 2.5 for a y coordinate. However, I need you to understand, if I put in a large enough number for x, my calculator is just going to tell me 2.5, even though it's not. It's going to round it to 2.5. So this is y is equal to 5 over 2, because as x approaches infinity, y approaches 5 over 2. And there's a rule, and what I'm going to do is I'm going to leave the page that we're looking at up on the right-hand monitor screen, and I'll show you the rule. So you'll notice if you look at the first function that the highest degree term on the top is 2. It's a quadratic polynomial on the top. And the highest degree term on the bottom is degree 1. It's a linear. And the rule, and this is in your notes, however, I think your 3 rules are side by side, correct? Okay, I don't have a way to format it nicely here, so I'm doing it this way. If the degree in the numerator is more than the degree in the denominator, then there will not be a horizontal asymptote. There's a reason for that, but I find it unimportant in this course. Okay? Again, like I said earlier, sometimes we just have to rely on rules. We have to go away from the concrete into the abstract and just say, this is how it works. Well, not how it works. This is what happens. The workings of it are not important. When you take a look, so there's no asymptote, when you take a look at this one, number 2, f of x, the degree on the top is 1, the highest exponent on x on the top is 1, and the degree on the bottom is 2. There's nothing special about 1 and 2 other than the fact that the numerator degree is smaller than the denominator. And if that's the case, the x-axis will be, y equals 0 will be a horizontal asymptote. When you take a look at the third one, g of x, the degree on both of them are the same. And when that's the case, the horizontal asymptote will be at, now you can add something here if you need to, but I'm saying at the coefficient of the numerator over the coefficient of the denominator. I'm talking about the coefficient of the highest degree terms. And the reasoning is, I can go back and just show this to you briefly. The reasoning is that at very, very large values of x, 9 and negative 10 and negative 2x and negative x, none of those count for anything of value. Because you're looking at an incredibly large value of x, it's going to be the highest degree term that kind of rules the roost. And that means that the x squareds would cancel, and it's 5 over 2. And that's kind of how we evaluate limits in calculus. And 5 over 2 is 2.5. So that's how you determine the equation of a horizontal asymptote. Any questions with those 3 rules or that warm-up? All right. So now the next lesson that we're covering, it's also a very short one, is called Connecting Equations and Graphs of Rational Equations. So what we want to do here is relate the roots of a rational equation. Roots are solutions. The solutions to a rational equation. What's a rational equation? A rational equation is an equation that looks like that. It's an equation that has an unknown and it's got a rational expression in it. Another rational equation would be that one. Keep something in mind. You were taught last year about rational equations and how to solve them. algebraically. According to the curriculum in this course, you're expected to know how to solve them graphically, but there's no emphasis on the algebraic side. I'm going to go through the algebra anyway. I think it makes you a better math student, and you never know when it might come in handy, because solving graphically is sometimes more trouble than it's worth. Because you've got to find window settings, and the graph may be something that looks unfamiliar to you, so you might not know what its behavior is like. Listen, if I go back, if I were teaching grade 9, and students in grade 9 were allowed a graphing calculator, or grade 6 or 7, and I teach them how to solve this equation. I mean, we know what the solution to this equation is, don't we? 2.5. Move the 5 over by adding 5 to both sides and divide by 2. If I was a really lousy math teacher, and I just said, you know what, I'm going to give you guys graphing calculators, follow my lead here, and I'll show you how to find x. And the kids are all attentive, they're looking at their graphing calculators, and I go, do this. Take y equals 2x minus 5. Mr. Way, what does that mean? Don't worry about it. Y equals 2x minus 5. It's going to give us a graph. What is that? Don't worry about it. So then go zoom 6, just because I'm telling you to. And we're going to find out where that crosses the x-axis. How do we do that? Well, we go to the calculate menu, and the kids are all writing down the steps. You choose 0, y, because I'm telling you to. Just shut up and do it, right? And scroll so your cursor is to the left of that point where it crosses that horizontal line, and then hit enter, and scroll to the right, and hit enter, and hit enter. There's the answer to the question. Write it down and move to the next question. You agree I would be doing, I hope you agree, I would be doing those students a disservice, right? I wouldn't be teaching them anything about math. But the point is that any solution to an equation that's of the form a function equals 0 will always be the x-intercepts of the graph of the function equals to y. So when we are asked to solve these graphically, we can use that idea. But before we do that, let's solve this algebraically to remind ourselves how to do this on paper. I'm going to rewrite it, and I think you know me by now that I'm kind of a weirdo this way. I want to rewrite it this way so that it's very clear that x is a numerator of a fraction and 5 is a numerator of a fraction. This allows me, although I don't need to do this, it allows me to put the x over 1 and the 5 over 1, and everything's nice and tidy and lined up. Okay. When I teach this to Math 20 students, I tell them, look, it isn't that you have a set of rules for solving this type of equation. The bottom line is fractions are things that make things difficult. So get rid of fractions. Get rid of denominators anytime you can. And that's going to work with trigonometric equations or logarithmic, with any equations. So we accomplish that by multiplying each term by x plus 2. Now, sometimes I'll just say multiply the left side and the right side by x plus 2. I hope you understand that there's really no difference between saying those two things. The bottom line, however, is that we're going to end up with x squared plus 2x plus 6, because these cancel, equals 5x plus 10. And now we're in the realm of a Math 11 equation. It's a quadratic equation, which should be at this level a piece of cake for us. Just double check my work here. Looks okay. So I'm going to zero this equation because it happens to be quadratic. It's going to be negative 3x on the left because I have to subtract 5x, and it's going to be minus 4 on the left because I have 6 minus 10 equals 0. It's factorable. X minus 4, x plus 1, which means we get two solutions to this equation. X is equal to 4, and x is equal to negative 1. A question for you, though. Is it possible to have extraneous roots for this type of equation? Meaning, do you think it's possible for me to do the work right and get a solution, but it doesn't work? Look at the original equation. What is a value of x that a person could get for this equation that would not be allowed? Do you know, Will? Negative 2. Because negative 2 is a non-permissible value. So all we have to do is confirm that neither of these numbers are non-permissible values. Right? In the original function, there is an over x plus 2, which means it isn't written here, but it could be x is not equal to negative 2. So if you did your work on a question like this and you get negative 2, it's not an answer. Now we're going to solve it graphically. Well, I'm going to solve it with the x-intercept method and then show you that I don't particularly care for the method. In order for me to solve this with the x-intercept method, I have to zero the equation. Because what I'm thinking now is y is equal to this thing, and an x-intercept is where y equals 0. This is why this works. We've talked about this numerous times in other units. I don't care for this method. I'll show you another method in a second. Sorry, I was just thinking if I wanted to say something else, but I've changed my mind. So I'm going to graph y equals x plus 6 over x plus 2. I know that that looks, at least on this calculator, like it's x plus 6 divided by something. It's not. It's x plus 6 over the x plus 2. And then I have minus 5. And since it's equal to 0, I'm going to be looking at x-intercept, so I go zoom 6. Again, I just want to point out to you that the fact that it looks like what it looks like is not something you care about. What you care about are the x-intercepts. And I don't feel we need to spend a lot of time with this. I'm going to find the x-intercept on the left. Go to your calculate menu and choose 0. Enter to the left. Enter to the right. Hit enter. You get negative 1, which was one of the solutions we got, right? The other solution we got is 4, and if you were to repeat the same process, you get 4 there. I'm not a fan of finding x-intercepts, and I believe I've talked about this before, because if the function is very steep at that x-intercept, it's difficult for me to put the cursor to the left and to the right. Okay? So what I would prefer to do is simply look at the original function and say, I'm going to call this y2, and I'm going to call this y1, and where they're equal is the solution. It's also easier for me to find intersection points on the graphing calculator because I just go enter, enter, enter. I just scroll in the right vicinity and hit enter 3 times. But just to briefly show this, the difference here would be that this would be 5, and up here it would not be a 5. Now I'm going to have 2 graphs now. There's the first graph. Here comes the second one. Well, now I'm going to find those intersection points. Again, I'll just choose to find 1. I'm close to the one on the left, so I'm just going to leave it there and go enter, enter, enter. And you get an x-coordinate of negative 1. When you use the intersection method, which is what I prefer, it's just the x-coordinate. You don't care about the y-coordinate. Any questions with example 1? All right, let's jump ahead now. And let's look at example 2b. We'll do 2a in a second. Now that we're kind of focused on using our calculator, let's solve this equation graphically. I am not going to zero the equation to get one function so I could find its x-intercepts. Let me be clear. You need to know that that's a possible path that would lead you to a correct solution. You can be asked about that on exams. I would just prefer to say y1 equals y2. This is going to get a little ugly because we're going to have 2 rational functions now. Before we had 1 rational function and a number. Now we're going to have 2 rational functions. Each of these rational functions has an asymptote, so it could be a little ugly to look at. What do we have? X divided by, in brackets, 2x plus 5 plus 2x, And then we also have, in brackets, 8x plus 15, close brackets divided by in its own set of brackets, 4x plus 10. Double check everything. It looks okay. Graph. I was already on Zoom 6, so that's fine. There's the first graph. There's the second graph. I want to point out to you the confusion here. This is why I'm doing the graphing first. I think it's quite obvious. Where one intersection point is. I mean, right in here, yes? But, you know, are these intersecting down here? Or are they intersecting up there? It's not as clear, is it? And honestly, I don't know. They may not intersect at all. It could be that these things are always going to be separated from each other here, no matter how far down you go, and they're always going to be separated from each other there. I don't know. And this is the frustrating thing about solving things graphically. I will admit, if you did it with the x-intercepts, it might be more obvious, the solutions. Anyway, let's see if we can find them. So I'm going to go to my Calculate menu and choose Intersect. I'm right here, so I'm just going to go Enter 3 times. One of the solutions is 0.75, 3/4. So x is equal to 3/4. And now I guess I'm going to repeat the process. But here's what I'm going to do. I'm going to scroll down here somewhere. And my understanding is you don't have to see the intersection point vertically, but you have to be in the right horizontal position. Given that these are both asymptotic there, this should do it. So I'm going to hit Enter, Enter, Enter. It just keeps kicking me back to 0.75. That's telling me I suspect that there is not an intersection point in this region here. It's not intersecting in there. Well, what about over here? Maybe it's intersecting there. Well, let's take a look. I have to navigate across that asymptote that they both have. They both have the same asymptote. There I am. So Enter, Enter, Enter. It just keeps kicking me back. So what this is telling me is I suspect there's only one solution, but I can't be sure because of the nature of the graph. Let's leave it there. Let's go back and solve it algebraically, which will confirm our suspicions, hopefully. I'll ask you guys a question first. Before I start to get rid of the denominators, which I want to do, what should I do? See, while you're pondering that, let me rewrite this equation. And tell you that it is a fatal mistake for you to multiply both sides by 2x plus 5 and multiply both sides by 4x plus 10. Why?
You can factor 2 out of 4x.
Right, and be left with 2x plus 5. So if you multiply both sides of this equation by both of those denominators, you're going to end up creating, a cubic polynomial, because that 2x is going to be multiplied by 2x plus 5 and 4x plus 10. This is 2 times 2x plus 5. I don't know if you were in my Math 20-1 class, you probably remember this. I mean, I had a big image, and it was just one word that said factor in rational expressions. And anytime we would do something and a student would say, I don't know what to do first, I'd bring that up. Factor. You always factor first. Because now I can see that I can multiply both of these sides of the equation by this. And that will clear the 2 and the 2x plus 5 on the right, and it will clear the 2x plus 5 on the left. So what cancels on the left is this, on the right, all of this cancels, and now you're left with an equation you can solve. We have 2x plus, this is 4x, so I'm going to multiply that 4x by the 2x plus 5 and get 4x times 2x is 8x squared plus 4x times 5 is 20x. So 8x plus 15. That's what you meant. Sorry, Ali. So that's the equation. 8x squared plus 20x is good. 8x plus 15, good. I'm sorry, I apologize. I misunderstood what you said or what you meant. So now we can zero this equation and get 8x squared plus, let's see, 12. I think it's going to be 14x. Can you confirm that? And then minus 15. Now, we can kind of cheat a bit here because we know that one of the solutions was 3/4, right? So that must mean one of the factors is 4x minus 3. And we kind of did this in polynomials. If it's 4x, this must be 2x. And it would have to be plus 5 in order to factor it correctly. So what are our solutions? Our solutions are x equals 3/4 and x equals negative 5/2. What's going on here? We couldn't find that negative 5/2, could we? It wasn't, our calculator kept kicking us back to that 3/4. What's going on here?
That's not a solution. If you put it into the original function, it would be given a value that couldn't be possibly made.
Right. We would end up be dividing by 0.
Yes.
When you take a look at the original function has a denominator of 2x plus 5, so there's a non-permissible value of the 0 of that factor. There's an asymptote there, in other words, in this case, which means this is not a solution. So we verify it algebraically. The two things you have to know how to do out of today's work is how do you determine the equation of a horizontal asymptote using those 3 rules where you compare the degree on the top to the degree on the bottom, and by hook or by crook, how do you solve a rational equation? Calculator, okay if you want. Algebraically, if you prefer. It's up to you. Okay? So you have a few questions to work on for practice for tomorrow. Tomorrow we are moving on to chapter 10. We're done chapter 9 now. Okay. I've got 2 to 11 and 14 as suggested practice. Again, I don't necessarily expect you to do every question, but I would expect you to sit back at some point and look at them all and go, wait a minute, that question looks a little weird. Maybe I better try that one.